So last time we had talked, we had been talking about ways to describe a function. And the first two attributes we talked about were domain and range. And then we had talked about next this positive, negative, and zero topic. That was all from last time. We're going to kind of continue on with our list and talk about some more descriptors. So the focus today is going to be on this idea of increasing, decreasing, and constant. So when we say increasing, what we're really talking about is if you walk along the graph from the left to the right, the increasing parts are when we're walking uphill. The decreasing parts are when we're walking downhill. And the constant parts are when the graph is flat. So let's look at an example to kind of illustrate this idea. So the way I like to think about this is I pretend I have a little man that walks along my graph, and he always starts on the left-hand side. I'm going to call this little man Hans, like he's some kind of Swiss mountain climber. That usually gets a laugh. Nobody laughed today, huh? Okay. Well, it's early. Yeah, thank you for your pity. So as Hans walks along the graph, this first part of the graph is uphill, so that part is increasing. When we get to here, Hans is now walking along a flat section. That part is constant. And then when Hans gets over here, we get to this part, which is downhill, so that's decreasing. Do we think we feel okay with what we mean by increasing, decreasing, and constant? Again, it's very visual. We're just looking at it from the graph. I'm going to skip the very technical description because what I want you to be able to do is look at a graph and tell me where it's increasing, decreasing, and constant, which I don't think that the technical definition really is going to help us much with. So we're going to just kind of do this informally like we've done here, but I think it's really practical and applicable, the definition that we're kind of given. Okay, so for the increasing, we're always, when we talk about these attributes, we're going to describe where it's happening, and the answer to where questions when we're talking about a function is its x-coordinates. So I'm going to look at the leftmost part of my increasing piece, which is negative infinity, and the rightmost part of my increasing piece, which is negative 2. Everybody okay with that idea? Sarah? Yes, I am recording. No, I appreciate you checking. I did it quickly and discreetly, but if you should please, I'm sure I'm going to forget at one point, so I don't mind you checking. Obviously, the infinities always get a parenthesis, right? And these transition areas, so the places where the graph is transitioning from increasing to flat, or increasing to constant, and then constant to decreasing, those don't get included anywhere. So we're never going to include those in any of those sets. So really, when we write these intervals of increasing, decreasing, and constant, everything's going to need a parenthesis. There aren't going to really be any brackets. So that's good. So the constant part begins at -2 and ends at 6. And again, we don't include the transitions, the places where it changes from increasing to decreasing to constant. And the last spot, the constant, we start here at 6, and we end here at, with the right arrow, at positive infinity. And again, infinities get a parenthesis, and the transitions don't get included either, so that gets a parenthesis. So we have that. Everybody okay with this one? Not too bad, right? Very similar to the positive, negative, 0. Probably the hardest part is keeping the two definitions straight. But if you use your mountain climber there, usually things work out okay. So we'll start the same way. We're going to first just kind of circle the increasing, decreasing, and constant parts of this graph, and then we'll write our intervals for those pieces. How many increasing pieces do we see here? 2, right? So Hans is walking uphill on this section, and then also walking uphill on that section at the end. So I have 2 increasing pieces. Where about, excuse me, where the graph is decreasing? How many decreasing parts do you see? 1. Everybody agree with that? So on that section, Hans is walking downhill. And then how many constant sections do we have? 1. This spot right in here is flat, so that's our constant section. Okay. So let's write our intervals. Since I have 2 parts of my graph that are increasing, I'm going to use 2 intervals. So I'm going to need to use a union there to connect them. That first interval begins with the left-hand arrow, so that's my negative infinity, and it ends at -2. And then for these ones, really everything gets parentheses, so I don't have to think too hard about that. My second increasing part starts at 5 and ends with the right arrow, so that's a positive infinity. And again, really everything's going to get parentheses when we do increasing and decreasing, so let's do the decreasing piece next. So that begins at -2 and ends at +1. And then my constant part begins at 1 and ends at 5. What do you guys think about this? Feels okay? Good. The next topic is extrema. So there's two types of extrema. We have maximums and we have minimums. Actually, the plural for that is maxima and minima. A single one is a maximum, an individual, or an individual minimum. If you have two of them, you'd say I have two maxima or two minima rather than two maximums. But I wouldn't be that picky. But just so we're clear, that's the grammar. And for the maximums and the maxima and minima, there's also two types. We have locals, and then we have the global or absolute. And again, I'm going to kind of skip formal definitions on these and just kind of show you with examples, because what we're doing with the maxima and minima, I'm just really expecting that you're able to kind of pick them out from looking at the picture, less concerned about like doing anything rigorous proof-wise with it. So I just want you to be able to identify what they are and tell me the values or the location. So let's do an example here. Okay. So when we say a maximum, we're really talking about like the top of a hill. And when we say minimum, we're talking about like the bottom of a valley. So if I look at this graph, how many maxima do we see? 2, right? Those guys are both tops of hills. How many minima do we see? 1. This one right here. Please continue to participate. I want to, like, as just an aside, we don't learn by saying the right answers. You learn by making mistakes and getting corrections. There's nothing wrong with answering a question incorrectly. That is literally how you're going to get better at this. So, like, don't get frustrated. Continue to answer questions, whether you're getting them right or wrong. Okay? Obviously, we're trying to give right answers. But don't be frustrated when you get wrong answers. It's okay. Okay? So, please, continue to participate. Don't be frustrated. Okay. Everybody feel good about what I mean by a max and a min? Okay. So, a local is any one of these max or mins. The global is the highest of our maxima or the lowest. I shouldn't say that. I should say that it's the highest point or the lowest point. That's the way I should probably say it. And PT, I've just abbreviated point with PT. So if I look at this picture, do I have a global maximum? Yes. Which one of them is it? The one on the left, negative 5, 4. So this is our global. So this one is a local. Like any maximum or any minimum is a local. Only if it's the highest point is it a global. So let's look at our minima now. Do we have a global? No. All of these points are lower than negative 2, negative 3, correct? Remember here, I said lowest point, not lowest minima. I started to write that and I corrected myself. So this is just a local because I have those ends going down. Everybody okay with that? So as an aside, suppose I have a graph that looks like this. What can I say about the presence of any global maximum or minimum? Kate, what did you say? Yeah, good. There isn't one. Why not? Yeah, there can't be a global because this arrow pointing up gets rid of all the global maxima, right? Can't have a highest point because that arrow pointing up. And this one gets rid of the global minima because you can't have a lowest point if that arrow is going down. You can still have locals. In fact, there is one each local maximum and local minima here. But there cannot be a global if you have one end pointing in either direction like that. That's a nice little observation to make. And really, the ends that the arrows point, whether they're pointing up, gets rid of any global maximum. And if the arrows both point down, gets rid of any global minimum. So you can tell right away just by the direction the arrows are pointing whether you can have a global maximum or minimum. Does that feel okay there? Okay. How much time do we still have? 10 minutes. I think we're going to stop here.